So let's go ahead and address the same equations that we derived in the previous class, but here we're going to do them in integral form. In the last class, we derived this equation right here, where we basically said for any quantity that you place in here, you can have substantial derivative will be you will have a convective derivative and a local derivative. Okay, so now if I wanted to do this in the integral form, the integral form is done as follows. So let's go ahead. Now I have, instead of the derivative, I will have the integral of the same quantity. This is Q times the volume. And I want to take the total derivative of this integral. Okay, so if I wanted to do this, this is over R. And I take the triple integral of this, the total derivative of Q times rho dV plus a derivative of this times the derivative of this. Remember, the volume can change as we move with time. So this is Q rho dt and the volume. Okay, so we're going to call this expression 1. We're going to call this expression 2. And let's work with each one of these expressions individually. Sorry, this is expression 1. This is expression 2. Okay, so expression number 1 says d dt q rho. And if I use the same equations here, where I have a substantial derivative, this is the same as a convective derivative and a local derivative, I can express this as using the same rule as follows. Q rho plus partial of Q rho dt. Okay, so now this is equal, let's go to the second term. This is the substantial derivative of the volume. This would be nothing else than the same expression. The only thing that we are changing is the volume plus partial of the volume respect to time. So now, if you realize, what I could do is I could multiply dV here, and I could divide by dV there, right? So this whole expression, if you remember, we derived it before. This is nothing else than the volumetric strain of the fluid particle. Okay, so then this whole expression, if you look at carefully, this expression and this expression, they look kind of similar, right? They're there, but they're opposite. Okay, one place you have the divergence vector on one side, the other one you have it the opposite. Okay, so now we're going to take this expression, going to plug this expression in here and this expression there and expand the whole thing. So then we have the total derivative of t over my volume R. Q rho d volume will be the triple integral of R. And the first expression is equal to V dot Q rho plus partial of Q partial of T dV plus the second expression rho QR divergence dV plus v dv. Now note that this quantity dv is a constant, okay? So therefore this term will go to 0. The only term I'm left with is this term, okay? In the second integral. Okay, this is the expression, this is the second part, this expanding this part right here. Okay, that's where I get this expression from. So now let's put everything together. Okay, let's combine all the terms, and you will see that what I can get here is the triple integral of R over the region volume R, partial of Q rho dt d volume. This is this expression, and I'm going to combine this expression with this one in one simple integral. And you will find this is dot q plus q dot v over the volume. Now, if you pay a close attention to this, you see I got my q there, I got my q there. So you can show that this is nothing else than dot q rho times v. And you can see that, right? Take the divergence of the first term times the speed, that gives me that, plus the first term times, then the first term times this, the gradient of that. So that gives me the same expression. Now, one of the interesting things about calculus is that we know the divergence theorem. So let me write this whole expression again. So this second term, that second term right there, we could express that as follows. This v q rho d volume. And then what you have with the divergence theorem, the divergence theorem states that the triple integral over the volume of this times any quantity will actually be the same as the quantity in the closed surface S times the unit times the area vector. Remember, dot. This is nothing else than the area vector. Okay, we express it like this typically. So if I apply this rule here, I can show that this is equal to the double integral over the enclosed surface. This is this, so this would be v times q rho dot n times ds. Okay, so that is the second expression. So now I can go ahead and place everything together and all the terms together, and what you have is the total derivative of this term will be the convective derivative over the volume plus the enclosed area S, velocity, that quantity q dot n ds. Okay, so this is how you actually do these problems, and this will be in integral form. Okay, so this exercise has been basically using this theorem. This is similar to the line the line integral that we talked about, right? You can have a double integral, and that gives you the line integral. So this is equivalent, but in 3 dimensions. The other one was just in 1 dimension. So this concludes the first topic of discussion, equations of motion.